Hello ladies and gentlemen, and welcome back to another lesson of probabilities. Now if you remember, this is where we left last time. We were given some data samples, x1, x2, xn, right here, and we were supposed to estimate the mean and the variance of the distribution, of the probability distribution they came from. And we reached this function over here, which we needed to minimize. And we asserted, actually it was a true assertion, that we can independently minimize this function in respect to mu and sigma. So we already performed the minimization in respect to mu, and we reached this estimate of mu, which is identical to what we were expecting and what we were learned in school. And also we were wondering if the variance estimate would also have the similar form we are used to. I don't know. Let's see if mathematically we obtain the same estimate, and we will also need to see whether that estimate is good or not. So I have summarized here this function that we need to minimize and the value that we have already estimate for the maximum likelihood of mu. Again, maximum likelihood stands for the value of mu which maximizes the probability of the samples occurring. So what would mu and sigma be in order for me to draw these samples if I draw n independent samples? Okay, so now we can perform the minimization in respect to sigma, and this was basically unfinished work from last time, and it should be a good exercise for you to do on your own. But for those of you who would like to just see the whole demonstration, here is me derivating this function. So I'm just gonna say f derived in respect to sigma maximum likelihood equals with, okay, so I have the derivative of a logarithm, and I get square root of 2 pi multiplied by n divided to square root of 2 pi multiplied by sigma maximum likelihood plus, okay, I get here, first we have to deal with the terms that are independent from sigma maximum likelihood. So I'm just going to write them right away to avoid any unnecessary complications. xi minus mu ml squared. Good. And this is multiplied by the derivative of sigma ml to the power of minus 2, which is minus 2 multiplied by 1 over sigma ml. Okay, so this should be equal to, I'm not going to do it this way, I'm just going to write again f derived in respect to sigma ml equals to n over sigma ml plus, actually minus 1 over sigma ml multiplied by, okay, I'm an idiot, it should be here to the power of 3, because so we have sigma ml to the power of minus 2 derived should be minus 2 sigma ml to the power of minus 3. So you subtract 1. So I get here 1 over sigma ml to the power of 3 multiplied by this nice sum over here. xi minus sigma ml squared. Good. So if we are going to determine the sigma ml value for which this value is minimized, we would have to write down this equation, and this is equivalent to n multiplied by sigma ml squared. I'm just multiplying by sigma ml squared above and below, minus sum from I equals 1 to n from xi minus mu ml squared equals to 0. And that leads us to sigma ml squared equals 1 over n sum from I equals 1 to n. Okay, so I have been a bit greedy here as far as space is concerned. It means that sigma ml squared equals 1 over n sum from I equals 1 to n xi minus mu ml squared. And if we go back one slide here, you should see that this is the value that we were actually expecting. Good. Now the problem is, how do we know whether this is a good estimate or not? Well, this, the variance, depends on a bunch of variables that are drawn from a probability distribution. And remember, mu ml also depends on a bunch of variables that are drawn from a probability distribution. All these values have an expected value. So for those of you who are not familiar, E of xi equals, or even better, E of f of x equals integral from minus infinity plus infinity from f of x p of x dx. So basically I'm integrating over the whole R, and I am making the product between the value of the function and the probability of actually getting that value. So the probability of the function at that point and the probability of x being located at that particular point. And you can imagine that we would have an expected value for sigma squared ml, and this value should be equal to, let's say here, the real variance. I would just use this notation for the true variance. True variance. So is this the case or not? We shall see in the next tutorial, so please stay tuned. This was me finishing the business from last lecture. You should go ahead and see that one if you haven't done so, because it explains how I get to this function over here. So I hope you guys liked it, and I will see you guys in the next tutorial, where I will explain why this is a bad estimate and why here you should have 1 over n minus 1. Okay.